Okay, so I'm going to present something that I have not heard yet on this talk. So people are working on mixed precision. I'm working on something a bit on the opposite side, but trying to ensure properties of solvers such as accuracy and reproducibility. So this is joint work with a team in Japan that are specialized on verified computing. So let me briefly go to motivation, briefly and quickly. So myself, I'm working, I'm more work associated to dense linear algebra. So this is sort of stepping in somebody's field, but I'm glad to be here because I may get some feedback or maybe I will get some cases to study. When I developed this BLAS library for accurate and reproducible computations, I noticed that my library works very well for memory-bound operations. So intuitively, I started looking for iterative solvers because they are memory-bound. And what comes from my studies, here in table, you can see a simple preconditioned conjugate gradient method when I use Jacobi preconditioner, and we report residual of when we try to solve a system of linear equations with 3D Poisson equations with 27 stencil points. We have one core runs and 48 core runs, and we compared to the MPFR library. So we implemented it with about 2000 bits of intermediate precision. Okay. And I still hearing me because I'm getting some strange messages that I left the meeting.
No, we can hear you
fine.
I'm sorry. So what we found that we can see that there is some inconsistency. Inconsistency in which sense? Our solver still converges, but residuals are slightly different in terms of number of digits that we were getting, and this inconsistency we highlighted in bold color, and we were observing them on different cores. Usually, when we implement some applications, we try to have something to compare with, for instance, on one core or sequential execution. Looking at these results, actually I got motivated to do something on iterative solvers in such a way that we will be getting the same result on one core and 48 cores that would be actually comparable to MPFR, but MPFR is actually single-threaded and very slow. So this was the initial idea of this. And further in the studies, we discovered that even number of iterations may vary. So for instance, we took some matrices from suit sparse matrix collection. We tried to take matrices with different condition numbers, number of non-zeros, and we made different experiments using pure MPI implementation, everything done by us, no PETSI and other libraries, MPI plus OpenMP tasks, and we use two clusters. One is Skylake-based cluster with OmniPath interconnect in Barcelona called Mare Nostrum 4. Here we have this result, and the other one is pretty much old cluster, like 10 years old clusters that is in-house. And we can see that even number of iterations is different. So my goal, my aim here to have the same the same residual in values independently on parallelization strategy as well as number of iterations. And to tackle this, I will be relying on two solutions. One that I developed myself, it's called exact BLAS, means fast, accurate, and reproducible as much as it can get. And the other one is Ozaki scheme BLAS, which is very quite promising Japanese team. Then I will try to apply the solutions into preconditioned gradient method. So let's begin by at first look on computer arithmetic, because we are dealing with approximation of real numbers. So it means that we truncate some parts of numbers, which called we do rounding, and due to that we lose some property like associativity. So here on this example, it can be clearly seen, and that means also to us that the result of floating point computations in parallel environment with different architectural settings, scheduling policies, etc., depends on the order of computations. And furthermore, if we use parallel implementations, they converge to the solution, but they may produce different, slightly different or significantly different results. We are looking here on reproducibility, meaning ability to get identical and accurate results from one round to another on the same or on the same data, on the same or different architectures. And here we will be touching two different architectures, CPUs and GPUs, and also different programming environments. This approach that I promote is the study began in 2013, and we started looking what can we get, and we were looking on it from accuracy perspective. So we wanted to have correctly rounded results. So it's actually the best possible approximation of to a real number. And we took a look on Coolidge accumulator. And this accumulator is can be viewed as projection of the whole set of floating point numbers on some vector, where we divide it into chunks and we accumulate numbers to different chunks depending on the exponent. So when number arrives, we check exponent, and then we chop number on two parts and we accumulate to two different chunks that are called digits. And it's primarily was designed for very severe cases. So it means that its overhead is a bit high because memory consumption, a number of flops, conversion from floating to integer. So we modified it, and by adding carry bits per each digit, so we can accumulate up to 2,000 numbers to it before normalization. And we look on another solution also that is called floating point expansion. Basically, it's a short vector of doubles where we will be storing results. And since we are interested in correct rounding, we need to keep track on error and on result and error. And we do it thanks to two-sum. So in two-sum, we add two numbers, we have result, and by using IEEE operations, so we can recover error in S. When we know the order of operands, we can apply fast to-sum. Fast to-sum issue, from my experience, is much better for CPUs. For GPUs, it does not work very well due to branches. Then we glue this together, try to tune to different architectures like CPU, GPUs, Xeon Phi, and with such ideas that we try to use as much as possible FP floating point expansions and as little as possible superaccumulator because it's heavy. So when we get a vector, we divide it into different chunks, we throw numbers on threads, and we keep adding them without sorting, without any tricks. And when we see that capacity of floating point expansions is not enough, we involve superaccumulator. And it usually happens that we have one superaccumulator shared between group of threads or within one warp, and then we do reduction within one node or within one block, and etc., etc. And finally, we end up with one superaccumulator that we round to target precision. So thanks to that, we keep every bit of information. The other solution is Ozaki scheme. Ozaki scheme is quite nice and suitable for dot product and matrix multiplication, and it also based on error-free transformations like two-sum, and it works as following. We split a vector into chunks, and we split it each element of it. For that, we need to find maximum, and from maximum, we determine how to chunk it. So here's an example when we have multiplication of 123 times 456. You see how we can slice these numbers in order to perform multiplication. And after that, we add. And we'll have 8 additions. It's possible also to determine what kind of accuracy we want, and then eliminate some of those products. After that, we perform these products, and then we gather results together. So it can be viewed as OpenMP fork and join. At the beginning, we have input computations, we slice them, we engage operations, and then we merge them together. And in more details, it is as follows. What is interesting is actually here. So we slice numbers in such a way that Their multiplication will be error-free. So it means that there is enough bits in those slices. They are still double precision, but a significant number of bits is designed in such a way that we will not have underflows or overflows. And this means that we can freely and safely engage optimize blast routine. So this is very important and key selling point of that approach, because we can use QBlast and KL library without any side effects, pretty much. And in order to merge everything together, we rely on near-sum algorithms that can ensure also correct rounding. Let's take a look on our test case, which is preconditioned conjugate gradient. We know it pretty well, so our idea was to ensure reproducibility and accuracy of each underlying kernel, and thanks to that, we would be able to ensure reproducibility of the method as whole. And the obvious sources of non-reproducibility are those kernels that require reduction or some parallelism, so SPMV, dot product, and XP. XP is rather simple because we can use FMA. It's actually element-wise product, and then we sort of enhance a bit accuracy. For the rest, our goal was to combine arithmetic solution, do some reorganization of operations, so in terms of programmability, and if possible, sometimes it was possible to do sequential execution. So we wanted to have light and lightweight approaches. In case of SPMV, we occurred one situation that we had this A times B plus C times D product, and a compiler can actually choose here 3 different paths. Either multiplication separately and then addition, or one of a multiplication and then FMA. So we injected explicit usage of FMA instruction to get some deterministic execution over here. And we have 2 solutions, EXBLAST and Ozaki BLAST based, and then one that was sort of derived from EXBLAST is based on FPE E of size 8. And for the main actually challenge was dot product, and to make it, to optimize it, to make it runnable on different architecture, we pretty much leverage and extended exact summation, so exact reductions that we developed already, and we introduced 2 product to this algorithm. And 2 product is multiplication of 2 numbers with possibility to recover a result and error. And it requires only 3 flops thanks to FMA. So FMA will do all the underlying operations exactly, and then we will have only 1 rounding at the end. And here's algorithm how it works. We have some local product. We apply 2 product. We accumulate a result to 1 floating point expansion and error to another one. Then we merge floating point expansions from different threads into 1 per process, and we conduct MPI reduction using this procedure that accumulates numbers to floating point expansion, and then we round to the target precision. We also studied, we implemented it, and then we got some critics because it's not robust, and in computer arithmetic, people want to have some rigorous solution, and we just studied for ourselves how good we are, or rather how much accuracy is required. And so we set here 8 digits, and we tested with some matrices with quite high condition number, 10 to the power 15, and here 10 to the power 9, with some different number of elements. So we can see that most frequent number of digits that we will be using for dot product, and we printed a maximum number of digits utilized for each dot product was actually 3. Sometimes, or rarely, we need 5. So it's there is still a possibility to optimize. So and the results actually were very nice and very nice for 3D Poisson equation over here on 768 cores. We had here relative normalized time. Showing some scaling, and overhead is at most 5% for this optimized strategy and 25% for the pure EXBLAST solution. When we look on Ozaki scheme, so here we did also some optimization, because when we have this multiple slices of dot product, calling each of them would be a bit expensive, so we decided to glue them together and do and invoke gem, which actually gives us a bit more performance boost, and it turns to be quite nice. Sometimes we have this is example on the case when we have 4 splits of a vector, each element of a vector. And we overall strategies here, we are speaking already for CG. We have not yet injected preconditioner to the solver. We tested on 2 CPUs, actually one CPU Skylake and another one accelerator Xeon Phi. We used different matrices from suit sparse matrix collection with different number of non-zero elements and condition number. We had here much tighter criteria on termination, 10 to the power minus 16. And in the table, we pretty much compare both methods. When EX+ based and native without FPEs, meaning was mainly tuned for CPUs. So here's the results that we can rely, and then we compile it for KNL. We compare with Ozaki solution, and we can see that it's like it depends on the situation. In 4 cases we are better. In 4 cases Ozaki is better. So it's really depends. This first matrix needs to be examined even further. How does it work? From my experience, when we look FPs, we can even lower our performance overhead. For instance, for this case, 0K performance overhead on single node was about 40-50%. So it's really advisable from to you. So just a few words. I showed you 2 methods that can be applied to ensure accuracy and reproducibility of iterative solvers. Depending on the case, we can have either a few percent, 20%, 5% overhead, or up to 20 times. Ozaki scheme is particularly interesting since it allows tunable accuracy. We still need to examine it, and it's efficient because we can use underneath vendor-provided implementations of BLAS instead of EX+ when everything should be implemented pretty much from scratch. So at this, I would like to thank you for your attention, and sorry for these disruptions at the beginning of my talk.
Thank you very much, Roman. First, I have to apologize to you. I said you are from KTH. You are actually from Sorbonne University and Fraunhofer. So for that, I was looking at some old website. Thank you for the talk. There is one question. Given nearly order of magnitude performance difference between bfloat 16 and binary 32, can you leverage it for reproducibility?
Yes, I see your point. So we actually take we have not yet touched bfloat 16. We were looking on half precision, and particularly how can we use TensorFlow and get or ensure some accuracy of results. And this is still ongoing work, but we actually experienced some interesting facts that, for instance, when we use FP6, so we want to get a result in FP62 precision, but we use half precision input data plus results 32. We notice that Tensor Core gives us round towards 0. So we need to be careful on this new hardware. They give enormous power, but there are some warnings that needs to be taken into account. We're working also on this, but we don't have yet results. So this is work in progress, what to say.